Okay, I think probably we ought to continue at this point. And if there are any questions, I would encourage you to say something in chat, for instance. But essentially, we went through just a simple example of some data set that we produced of people's ages and years of university education, where we thought maybe there would be some correlation between how old people were and how much education they had attained. And indeed, we do see here by the slope of this line, it's slightly positive. This gives us some simple model that would allow us to project our data set to try to understand something. And if we looked at, again, for instance, the slope that we saw up here, this would tell us that based on our slope with a slope of 0.21, that for each year of someone's life, we would expect that they would have gotten approximately 0.2 years more university education. And so that would be the kind of spread based on our data set that we have here. And our intercept here shows a value of about minus 0.8, which means that if we were to project this line down to an age of 0, it would intersect the y-axis at a value of minus 0.8. So that's the meaning of the A and B values here. And this is an example of how we can use them to make a plot of some data to fit a trend line to our scattered data set. Okay, let's move now to our next topic, if there aren't any questions, which is about linear correlation. So that's the linear correlation notebook, which you can just double click to open up. Again, here, the idea is that often we might think or anticipate that there could be some relationship between two values, for instance, age and number of university or number of years of university education. And that can be the case, but of course, there are other things in which we expect relationships to not necessarily be positively correlated. So, I mean, one example, I suppose, could be age and then life expectancy, or number of years expected that you're going to continue living. So most situations, the older people get, the fewer years of life they might expect to have left. And then you would have a negative correlation with something like that. And in some cases, you may have no correlation whatsoever in terms of the relationship. So what we're doing here in our next section here about the linear correlation is basically calculating how well our data fit a line, or how well they match a linear relationship between the two parameters. And we're going to do this by calculating a correlation coefficient with the lowercase r. It's also called Pearson's correlation coefficient, or the Pearson correlation coefficient. And it ranges between 1 and -1. And then here in the figure are a few kind of examples of the values of R for different distributions of scattered data points. So you can imagine the X and Y axes aren't shown here, but you can imagine that if they were here, this would be looking a bit like what we had just seen. So value of 1 would correspond to a data set where there's a perfect linear relationship between the X and Y values. Good example of this for geological terms would be things like isotopic age, where you can often plot relationships between the radioactive decay of different isotopes, and they tend to plot along a nice clean line if everything is working properly. So for geochronologists, this is often, you'll see like plots where they have different contour lines and things that are often based on data sets that pretty much fall right on a nice straight line. More often than not, geological data looks more like some of these other options here in the middle, where there's a bit of scatter, but perfectly falling on a line would give us a value of 1 if the slope is positive. If the slope is negative, a perfect correlation with a linear relationship would be a value of -1 for the R value. So the correlation coefficient would be -1 in that case. And for the things in between, the less and less they look like a line, the closer they go to 0. So away from either of the other ends, and 0 would correspond to the value for a random data set where there is no linear correlation. What you can see here is that the actual slope value doesn't matter itself so much other than for a value of 0. What is happening here is essentially a measure of how linear is the data set. So if the slope is steeper or more shallow, as long as it's a positive slope, you'll get a value of 1 for the R coefficient. And if it gets negative slope, then as long as the slope is negative, it doesn't matter how steep. If it's a perfectly linear behavior, you'd have a -1 value. And then for lots of other things here, different functions of different shapes, you can see the values are all 0 in this case, because none of these are really following a nice linear pattern. So of course, a bunch of points scattered around a circle, it's not a big surprise that its expected value for the R, for the coefficient would be 0. How we calculate that is shown here. It looks sort of in a way like what we had dealt with before. There's some summations. So here we're summing up the values of, in this case, it's each individual value of X minus the mean value of X. So we sum that up. And the same thing happens here. It's the individual values of Y minus the mean of Y. Those are all multiplied together and then summed like we saw before. And here, basically, we're doing the same thing, except we're taking the square root, and the summations in this case are squared and multiplied together and summed. So if we wanted to take a look at how linear our last data set was, that's something we could do now using this equation. The thing is, I don't want to have to refer back to that equation on this notebook page, so I'm just going to double click on the markdown cell here, and I'm going to jump back to our least squares example. And I'm going to add here a markdown cell and just put this equation in it. So we have our equation. We can get rid of this one. Here's our equation for the correlation coefficient R. Let's go ahead and calculate what the R value is for this data set. I think you can see here, it's sort of linear. You might expect, like, based on the fact that the trend line's not horizontal, so it's maybe not totally random, but it's also not that these points are falling really close to the line. Some of them are kind of close, but others are a bit far away from the line. So already we might have some guess that we're going to have a positive value for R because it has a positive slope in this relationship, but it's probably not going to be a value of 1 or that close to 1, probably something like, I would guess, I don't know, 0.5, 0.3, something like that. But let's calculate what our R value would be. Now, in this case, to sum things up, we can do things a couple different ways. I think what I'm going to do is calculate a top term and a bottom term. And I'm going to do the sums using a for loop because I want to go through each value of X and subtract away the mean value. We don't necessarily have to do that with a for loop, but it might be easier for you to follow if we do it with a for loop because it's more like what we would have introduced in GeoPython. So let's start with the top. And we'll say top sum equals 0 and bottom sum equals 0. Okay. So let's we'll initialize our summing variables. So that means we're just going to set them equal to 0 so that every time we go through this loop, we'll just add whatever the current piece is to what we had before. So then we should say for I in range, len, and we'll take ages because we have that still here. So this is just going to go through whatever number of ages we have and do some stuff. Our summation is going to be the value of age for the current, so like age of I, and minus the mean of the ages. So we can say, for instance, here, our top sum equals top sum plus And then this should be ages of I. So that's going to be this x of I equivalent. So that's our ages of I minus age is ages dot mean. We could also use our mean function if we had that available, but that's not here right now. So we'll just do ages dot mean to get the mean value here. Now let's put this in parentheses because this is multiplied by the equivalent, which I'll also put in parentheses for the years of univ variable. So that's 8 years of univ of I, so that's y of I, minus years of univ dot mean. So that's going to then do this summation for us because we'll go through our for loop. Each time we're going to multiply, well, we'll calculate this difference, xi minus x mean, yi minus y mean. That's going to happen here. Multiply those two things together and then sum it by adding that to what we had from the previous time. So the first time through, the sum is equal to 0. We just add the first value here. And each time through the loop, it goes through each value of x and y and sum things up that way. Bottom sum works pretty much the same way. Bottom sum equals bottom sum plus. And here now we're going to have xi minus x mean squared. So let's just take what we had here, which was our ages of I minus ages mean squared. And then that's going to get multiplied by, and I'll just copy this thing as well, like I did before. And then we square that. So that's our yi minus y mean squared. That summation will all occur. And then once it's all done, we just need to make sure that we remember to take the square root when we calculate what the value of r would be. But at this point, we can calculate our top and bottom sums. And then we can calculate finally what our value of r would be here. And that is simply r equals top sum divided by np dot square root of the bottom sum. Now, of course, that's important because we have to remember to do the square root here, but we've basically done all the summations in this for loop. We finally calculate our r. And then we can print it out. So let's do print. We'll do another F string and correlation coefficient. Yeah. And then we just put our R value in there. And I'm going to go ahead and do 0.2F. So we just rounded off to two digits. So add in this little piece here after the variable colon and then the formatting for it. And if we run this cell, correlation coefficient 1.79, something went wrong because it shouldn't be able to be, should not be able to be bigger than 1. So what did we do wrong here? So we summed x of I minus x mean times y of I minus y mean, summed all that up. That should be our top sum. Ages of I minus ages dot mean times years of univ minus years of univ dot mean. That should be okay. And then bottom sum equals bottom sum plus ages of I minus ages mean squared. I think that also should be okay. And then top sum divided by the square root of bottom sum. Okay. I have to admit, I'm not totally sure why that didn't work. Let me see. Maybe I have to sum these two things separately rather than multiplying them together here. So I think actually this shouldn't be multiplied together, but should be added. So this, yeah, those aren't, no, those should be multiplied together. Well, let's do it like this. We can do bottom sum X and bottom sum Y. And our bottom sum X will only worry about the X summation. So that should just be basically whatever the sum is previously plus this piece here. So let's cut that. So it should just be ages of X minus ages of mean squared. And then our bottom sum Y should be bottom sum Y plus, and then I'll paste in this thing I just cut before, which is the years of univ of I minus years of univ mean squared. Then it should be the case that all we have to do is take the square root of bottom sum X plus times rather bottom sum Y. Let's see if that does it. I'm not quite sure what I did wrong, but that looks better. So correlation coefficient is 0.74 now. So it's actually higher than I thought. It's more linear than we might have thought. So that gives us then a sense of, yes, we see it's a positively correlated data set, and it's about 74%. I think this is maybe the way you can interpret this, that about 74% of the relationship can be explained by our line that we have fit to the data here. Again, you'll get an opportunity to play with this in this week's exercise. So yeah, I mean, we could basically take this now that we have it. We could copy our little F string here, put this on our plot if we wanted to. So we could, put it like up here or down here somewhere. Maybe we'll put it down here. So let's put it at like at X equals 28, Y equals 3. We can add some text. So let's do ax.text. And at X equals 28, Y equals 3. So that'll push this on our plot at that position. And we'll just paste our F string that I had before for the correlation coefficient. And if I run that, now you can see on the plot, the correlation coefficient 0.74 on the plot, which is sometimes a handy thing to have there to kind of show how well your data is explained by this linear relationship. Any questions at this point? Sorry about the minor mistake. Maybe that's a good learning experience for all of us, that sometimes it's easier to sum things up first in two different variables and then add them together after, or multiply them together after the fact. I should have thought about that because, yes, this should all be summed first and that should all be summed first, and then they should be multiplied together. Not what I was doing, which was multiplying the two things together and summing them at the same time. All right, if there's nothing here else, then we'll go to our last topic for today's lesson, which is about goodness of fit calculations. So this is basically a way of measuring how well some prediction fits a data set. So you can imagine if you had some numerical model to predict something like a geochronological age, and you had a measured age here with like a blue dot and some error bar, some uncertainty on the measured age, then what you could do is you could compare different predictions to that measured age. And maybe here you can visually see that, yes, this looks like this prediction fits the measured age pretty well because it falls within the uncertainty in the measured age. So essentially the two are not really able to be distinguished from one another within the uncertainty. Whereas over here, another predicted age doesn't fit within the uncertainties of the measured age. And so that's maybe not such a good fit. And we can quantify that. And that's what we're going to do here. The basic idea is that a nominal good fit would be one where your prediction's within the uncertainty in the measurement. And of course, if it's outside of that uncertainty, then that's not such a good fit. And that's basically what's said here in the start of this part of the lesson. So if we look at this example like this, essentially what we're doing is we might have maybe many different measured ages and many different predictions that go along with those measured ages. And we want to get some kind of number that indicates how well our measurements and our predictions compare to one another. And we can do that here by using something that's called the weighted sum of the squared errors. This is kind of wordy, so this is sometimes just simply called chi-squared because it's Greek letter chi squared. And what it is here is a summation of, here is an observed or measured age minus some estimated or expected value. That's the kind of prediction. So observation minus the prediction squared for one age. And then it's divided by the square of the standard deviation in the measurement. So if this error bar was representing, for instance, one standard deviation, then that would be the value that would be used here. And you would just square that for the one age. And you sum this up for however many ages you have. If you look at this equation in general, what you could see that is if your data are exactly matched by your predictions, so if your predicted values are exactly the same as all of your measured values, this sum at the top, or this difference rather at the top, will be zero. So if this observed or measured age, for instance, is the same as the predicted age, then the top term goes to zero. And if you have that be the case for all of your data that you're dealing with, then the chi value or the chi-squared value would be zero. That's as low as it gets. And the better fit here, or the quality or the goodness of fit for chi-squared is better for small values. So small chi-squared is what we're looking for a good fit. Of course, as things get further and further away from zero, that could reflect one of two things. One would be that the difference between the measurement and the prediction is growing or is bigger. So of course, if you make these two numbers, then you subtract them from one another, the more different they are, the bigger this top term would be then. Or if the standard deviation is really small, you can also increase the chi-squared values that way. So if you have very precise measurements, even if the measurement and the prediction aren't that far apart in terms of absolute difference, so like for age, if they're not millions and millions of years apart, but only even maybe 1 million or a few 100,000 years apart from one another, most of the time for geochronologists, we'd be pretty pleased with that result. But if you have really precise measurements, it might be the case still that the prediction doesn't fall within the uncertainty of the measured values. And that's typically because the standard deviations are very small, which occurs for precise measurements. So there's a kind of two different ways in which you can make things blow up. But since this top is squared and the bottom thing is squared, the chi-squared values are always going to be positive or zero. So that's just something to be aware of. I think I've more or less explained the kind of text here. I suppose the one thing that I didn't mention here is that if the standard deviation value is exactly the same as the difference between these two values, between your observation and prediction, that would mean in terms of our picture here, you'd be right at the end of one of the error bars, either here or here. Then you're going to get a chi-squared value of 1, because basically this term on the top when you square it, would be the same as the thing underneath it, which is going to give you then a value of 1. So you can see that as long as your value is between 0 and 1, it would be indicating that you're within the uncertainty or the standard deviation of the measured age data set. That's kind of explained a bit further here. One thing to note is there's several different forms of this equation. And one that I kind of prefer to use personally is what's shown here, and that is to divide whatever value you get from the chi-squared equation by the number of samples that you have. So if you divide by 1 over n, the benefit is that this will give you a sense of, on average, whether or not your predictions are within the uncertainties of your measured data set. So when you sum things up here, if you always have values, let's say, that are putting you right at the edge, 1 standard deviation away from the measured value, you're going to have a value of 1, and you sum that up for, let's say, 20 ages, your chi-squared value would be 20, because it's just going to be 1 plus 1 plus 1 until you get to 20. If you did the same exercise here, you would get, again, a summation that goes to 20, but then you would divide by 20, which would tell you then your chi-squared value is 1, which gives you an indication that on average, your data is right at 1 standard deviation away from the mean. Doesn't mean that they're all within the uncertainties, right? Some could be very close to the mean value, others, or to the measured value. Others could be further away and outside of the error bars, but at least this gives you something that's a bit easier to interpret, because the value of 1 or lower means that you're on average within the uncertainties of your age data set or your whatever data set. And if it's a value greater than 1, it tells you that you're on average beyond the uncertainties of your data set. Now, because of the time, and I think the challenge it would be to come up with a good example here, maybe I'll skip over demonstrating this for right now. But again, you'll get to do something with this in the exercise for this week. So you will have an opportunity to play with this equation. And if we have time at the very end, if people are curious, we can try to come up with another toy data set to play with our chi-squared equation. But yeah, if maybe, are there any questions? You could perhaps just say something in chat if you have a question at this point. Because if not, then I thought maybe it'd be good to go through the exercise for today or for this week. Let's do that. So exercise 2 is up on the GitHub repository. We have 3 pieces. No big surprise, because we had 3 components to this week's lesson, that we have 3 components to this week's exercise. Something about least squares regressions, something about linear correlation coefficients, and then finally something about goodness of fit. So that is what we're working on for the exercise for this week. Let's take a look at the notebooks. Okay, so our first problem deals with climate data. So this is actually carrying on from data that was produced in exercises 6 and 7 in the GeoPython course. Don't worry if you didn't take that, because I'll provide a data file here. But what we were doing in exercises 6 and 7 in that course was looking at climate anomalies and temperature anomalies in climate data. The idea being that we could look at things like how much the temperature deviates from a typical season and things of that nature. Or we could look at average temperatures and how much they vary in terms of a standard deviation. So we could look for the winter and say, what's the seasonal average temperature for the winter in different years, and compare them. So that's what we're going to be doing here at the beginning, which is basically we're going to do this least squares regression using climate data, where we have winter temperatures and summer temperatures that have been calculated from the years 1953 to 2019. And then we have also some standard deviations that we'll come back to using in problem number 2. The very first thing you need to do is make a copy or take your intro QG functions.py script from exercise 1 and copy it into the directory where this exercise 2 is, because we're going to be adding functions to it. Each week, I think we'll start out the exercise by copying the previous week's intro QG functions. There's not a really easy way to distribute that with the exercise each week. So it's best if you just copy what you had from the previous week's exercise, and then we'll start adding things to that. So you're going to, for instance, here, copy this script, and then there's just a simple set of tests where it runs to, let's see. Yeah. So it imports from your intro QG functions the mean, standard deviation, and standard error functions that you should have produced. And then there's a little test data set where it calculates what the mean, standard deviation, and standard error are, prints out those values, and then checks to make sure that they are reproducing the expected value. And if everything's good, you'll get a little message out that says, all tests pass, you're ready to proceed. So that's the first kind of step 0. After that, you've got a data file to read in. It's supplied as part of the exercise. You can, I think, click on it and see what it looks like in GitHub. And you'll see that there's years, mean temperatures, standard deviation in temperature for that season, and then mean summer and mean or summer standard deviation temperatures as well. Oops. So that's the data file that we're working with. You can take a look at that when you have a moment. After that, no surprise, your next step is to create a linear regression function where you'll calculate the A, B, and delta values in a function that you can call linregress, and you'll add that to your intro QG functions script file. And so this is how you're going to calculate your slope and intercept values. And then once you've done that, all you have to do for the kind of coding part in the notebook is just make it so that you import your function. So from intro QG functions, import linregress, you can just copy this here and paste it here in place of this not implemented error message. You can just delete that and paste the text there. Then this cell will check to see whether your linregress function works as it should. And if it does, then you'll be moving on to part 3, which is to calculate the regression lines for the summer and winter temperature data for 2 different time periods. So one is for the whole observation period, so 1953 to 2019, and the other is for the last 20 years. So just to look at the differences in the trends over those 2 different time periods. So you'll get some A winter and B winter values, A summer, B summer, and so on. And you'll just fill in here for each one of these lines a call to the linregress function that would give back the A and B values. Then you'll see a couple tests where print something out and says, here's the value that I expect. So you'll be able to see again whether your A and B are calculated properly. And then the last step is to plot up your results, where you take the temperature data that we have and you'll add to it these trend lines for the winter and for the summer. And you can then also add to the plot the slope, which is going to tell us on average how much is the temperature increasing from year to year. So we can see, for instance, from 1953 until 2019, that the temperature was going up on average by about 0.045 degrees per year. And so you can see along here a gradual warming trend. That is problem number 1. Problem number 2 asks the question of whether a line is a good fit to our data set. And so in order to determine that, as you could imagine, we're going to calculate what the correlation coefficients are. So we'll use the equation for the correlation coefficient R that we just saw to calculate correlation coefficients for our temperature data. And again, you're going to make this a function in your intro QG functions script file. And then you can just copy paste this command here to import it. And then this will allow you to test and see whether your Pearson correlation coefficient function is working as it should be. After that, You can then use it to calculate what the correlation coefficients are for the winter and summer and for the two 20-year time periods. And like we did before, you can then plot up your results, and things look fairly similar to what we plotted before. This time we'll do a scatter plot without the error bars because we're not using the standard deviations in calculating what the regression line correlation coefficients are. So we'll just do things like that, but you can find some details about how to format the plot here. And then finally, for problem number 3, we'll do some goodness of fit calculations. So again, you'll start out by making a function that you can put in your intro QG functions script file. Again, you have a test cell that will allow you to check and see whether it's working properly. And then you'll calculate the goodness of fit for the winter and summer. So you'll calculate some expected temperatures based on the regression line. And then you can calculate a goodness of fit based on those values as described. In the end, then there's just a couple small questions to ask you to reflect back on the plots that you've made and think a little bit more about what the meaning is of these different numbers you've calculated. So that is exercise number 2. It's not a tiny amount of work, of course, but I think this is more manageable, more reasonable in terms of it's definitely not as much as exercise number 1. You'll have been doing some things in exercise 1 that are similar to what you do in exercise 2 here. So that should also hopefully help with making this exercise number 2 feel a little bit less heavy. Do you have any questions at this point? Seems like maybe not. So, yeah, I think I don't have anything else in mind for today. I guess the only notebook that we really modified was this least squares notebook. And I would be okay to put a copy of this on the course page somehow. I'll have to think about where I will link it, but maybe I can just add a link so that you can download a copy or something like that, just so that you can see our toy data set that we played with and how we did all of this in terms of the calculation of the regression line slope and intercept and the correlation coefficient. I did not check to make sure that these are the correct values. So it would be good to make sure that you take advantage of that when you work on the exercise, because in the exercise, there are always some cases where you can take your functions you've created and use some test data sets where the known expected value is available to you. And then in that way, you can make sure that your code is working properly. I did not have in sort of independent calculation of what R and A and B would be for the data set we generated here. So it's possible there are some mistakes here. Just be aware. But if there aren't any questions, I suppose maybe we're done for today with the lesson. You've seen the exercise. I'll remind you that we'll give you until tomorrow at 5 p.m. to turn in exercise 1. So just in case you were having some problems, you still have a little bit of extra time to ask questions. So please feel free to jump on Slack and ask questions you might have, or take a look at the GeoPython course materials about how to use Git if you're having problems saving the notebook files you've been working on. I think other than that, we'll again be in the exercise session on Friday morning. So please feel free to come and join there. And maybe we can have a discussion on Slack about if there would be a benefit to having some kind of online question and answer session on like in the middle of the week. So we could possibly do that if you have like a if you would like to have a chance to ask some quick questions as you start working on the exercise before Friday, maybe we can do that, and let's maybe have that conversation on Slack. So I will add a question or sort of start a discussion there, and you can feel free to jump in and share your opinion if you think it would be useful or not to have an extra option to ask questions during the middle of the week. Of course, you can ask on Slack anytime, but if you would like to have a sort of brief Zoom session to clarify things on Wednesday, for example, that might be an option. But yeah, I think we're basically all set for today. So I will, I'll shut the recording down here. And if there are any remaining questions, feel free to stay on Zoom, and you're welcome to ask questions. And otherwise, we'll catch you on Friday in the exercise sessions. All right. So see you then.